Welcome to class, everyone. Grab a seat and get comfortable because today we're taking a massive leap forward in your coding journey. Remember when we first looked at the basic struct in C? That was your very first step into the world of abstract data types. You made a custom blueprint for data, which was awesome, but you still had to write standalone functions entirely outside of that structure just to actually do anything useful with it. Well, today we're graduating. We're moving from those basic abstract data types to object-oriented programming, which is, quite frankly, your ultimate passport to scalable tech architecture.
So, why are we dedicating a whole masterclass to this topic? Well, check out this number. Over 70% of modern enterprise software, and I'm talking everything from back-end cloud microservices to those mobile apps you use literally every single day, is powered by object-oriented or multi-paradigm languages. We're looking at industry heavyweights here, like Java, C++, Python, and C#. If you want to build software at scale, mastering these core principles isn't just an option, it's an absolute necessity.
All right, here's our syllabus for today's explainer. 1. Abstraction, hiding the complexity. 2. Inheritance, don't reinvent wheels. 3. Encapsulation, capsules of logic. 4. Polymorphism, the coding chameleon. And finally, number 5, the pop quiz.
Picture a classic Greek temple holding up our software architecture. It's supported by 4 massive pillars. And to remember these core pillars of OOP, just think of the phrase API: abstraction, polymorphism, inheritance, and encapsulation. Together, these pillars basically bridge the gap that those old abstract data types left behind. So instead of keeping our data and our actions completely separate, OOP creates what we call a class. Think of a class as a unified blueprint, housing both your attributes, which is the data, and your methods, which are the functions. And from that one single blueprint, we instantiate objects. Objects are essentially supercharged variables living right there in your memory. Let's break down each pillar holding up this temple, starting with the A.
Module 1. Abstraction, hiding the complexity.
Think back to your data structures and algorithms class. When you call a stack.push or a queue.pop, do you honestly care if the underlying structure is a dynamic array or, say, a doubly linked list? Not at all. Or think about how effortlessly we use Python lists. You make an empty list, you type mylist.append42, and boom, it's there. Did you have to write the memory allocation logic for that? Did you have to manually manage pointers or handle array resizing behind the scenes? Absolutely not. Python completely abstracted all that heavy lifting away from you, so you could just focus on solving your actual high-level problems. You only care about what the interface does, right? Not how it works under the hood.
And that's the real magic here. Abstraction completely separates the public interface from the messy implementation. In the real world, software architects actually use UML class diagrams to map out these interfaces way before anyone types a single line of code. This exact separation is what enables massive tech companies to scale up. Because of abstraction, a team of literally 50 engineers can work in parallel on the exact same project. A teammate can seamlessly consume your module's public API without ever needing to comb through your 1,000 lines of complex internal logic. That is the true superpower of abstraction.
Moving right along, Module 2, Inheritance, don't reinvent wheels. Consider my role in this classroom right now. I'm an instructor, but at my core, fundamentally, I'm a human. I have a name, an age, and, let's be honest, a highly concerning dependency on caffeine. Now, instead of writing an instructor class entirely from scratch and redefining all those basic human traits, OOP lets us just extend a human superclass and then add specialized methods to it, like, grade assignment or give lecture. Why does this matter? Because inheritance strictly enforces the DRI principle. Don't repeat yourself. It lets developers build complex, hierarchical frameworks almost effortlessly. Plus, unlike real life, code inheritance comes with zero inheritance tax and infinite reusability.
For example, take a look at this UML diagram for some banking software. If you look down at the bottom, you'll see the current account and savings account boxes. Notice those arrows pointing up to the base account class? Both of those specialized accounts are inheriting from that standard account blueprint. At their core, they're both just standard accounts, right? They've got basic features like a balance and a deposit method. But by leveraging inheritance, they bring their own unique, specialized attributes stacked right on top, and they do it without anyone having to rewrite all that original base code.
Up next, Module 3, Encapsulation, capsules of logic.
So we've talked about hiding complexity, and we've talked about reusing code. But how do we keep everything safe and organized? Well, it all comes down to the capsule. Like we touched on earlier, OOP lets us bundle data and functions together into a single unit, which is our class. This core idea, wrapping up your data attributes and the specific methods that operate on them inside a single protective container, is exactly what we mean by encapsulation. It just keeps the whole shebang neat, self-contained, and completely protected from outside interference.
And finally, we arrive at our fourth pillar, polymorphism, the coding chameleon.
Polymorphism literally translates from Greek to mean many forms. I like to think of it as a chameleon. Or actually, think about yourself. How you speak and act during a super formal job interview is, I'm guessing, very, very different from how you behave at 2 a.m. playing video games with your friends. You're the exact same human, but you're exhibiting completely different behavior depending on the context. Programmers absolutely love polymorphism because they get to have all these options without constantly changing their data types. In fact, you've been using this since day one without even realizing it. Think about the plus operator in Python. If you're doing numeric addition, 1 plus 1, it outputs 2. But if you do string concatenation, like the string hello plus the string world, it outputs hello world. The exact same operator is taking on a completely different form and behaving differently based solely on the context of the data it's handling. That specific concept, by the way, is known as operator overloading.
All right, Module 5, the pop quiz. Okay, class, attention please. Notebooks away. Let's see if you can apply this chameleon concept of polymorphism to a classic beginner puzzle. Here's the scenario. We have a variable a, which equals input first value. We have variable b, which equals input second value. The user types the number 1 for the first prompt, and they type the number 1 for the second prompt. What will print a plus b actually output? Take a second. Is it 2?
Nope. The answer is 11. Why? Well, because the input function in Python actually returns string objects by default, not integers. So Python's polymorphic plus operator doesn't see 2 numbers to add together, it sees 2 strings. It naturally just takes the form of string concatenation and glues the character 1 and the character 1 right together, outputting 11. It's a really perfect example of how operators change their behavior based on the object types they're interacting with.
And that, my friends, brings our masterclass to a close. We've explored how API, abstraction, polymorphism, inheritance, and encapsulation holds massive software architecture together, completely transforming basic data into scalable, secure, and reusable objects. But before I dismiss the class, I want to leave you with a provocative thought to chew on. If object-oriented programming structures allow human engineering teams to scale code bases so perfectly today, what entirely new paradigms or pillars are we going to need to organize the massive, instantaneously AI-generated code bases of tomorrow? Think about it. Class dismissed. See you in the next explainer.